The Distributed Computing Manifesto. Today, I'm publishing the Distributed Computing Manifesto, a canonical document from the early days of Amazon that transformed the architecture of Amazon's e-commerce platform. It highlights the challenges we were facing at the end of the 20th century and hints at where we were headed. When it comes to the e-commerce side of Amazon, architectural information was rarely shared with the public. So, when I was invited by Amazon in 2004 to give a talk about my distributed systems research, I almost didn't go. I was thinking, web servers and a database, how hard can that be? But I'm happy that I did, because what I encountered blew my mind. The scale and diversity of their operation was unlike anything I had ever seen. Amazon's architecture was at least a decade ahead of what I had encountered at other companies. It was more than just a high-performance website. We are talking about everything from high-volume transaction processing to machine learning, security, robotics, binning millions of products. Anything that you could find in a distributed systems textbook was happening at Amazon, and it was happening at unbelievable scale. When they offered me a job, I couldn't resist. Now, after almost 18 years as their CTO, I'm still blown away on a daily basis by the inventiveness of our engineers and the systems they have built to invent and simplify. A continuous challenge when operating at unparalleled scale, when you are decades ahead of anyone else and growing by an order of magnitude every few years, is that there is no textbook you can rely on, nor is there any commercial software you can buy. It meant that Amazon's engineers had to invent their way into the future. And with every few orders of magnitude of growth, the current architecture would start to show cracks in reliability and performance, and engineers would start to spend more time with virtual duct tape and WD-40 than building new innovative products. At each of these inflection points, engineers would invent their way into a new architectural structure to be ready for the next orders of magnitude growth. Architectures that nobody had built before. Over the next 2 decades, Amazon would move from a monolith to a service-oriented architecture, to microservices, then to microservices running over a shared infrastructure platform. All of this was being done before terms like service-oriented architecture existed. Along the way, we learned a lot of lessons about operating at internet scale. During my keynote at AWS Invent in a couple of weeks, I plan to talk about how the concepts in this document started to shape what we see in microservices and event-driven architectures. Also, in the coming months, I will write a series of posts that dive deep into specific sections of the Distributed Computing Manifesto, a very brief history of system architecture at Amazon. Before we go deep into the weeds of Amazon's architectural history, it helps to understand a little bit about where we were 25 years ago. Amazon was moving at a rapid pace, building and launching products every few months, innovations that we take for granted today. One-click buying, self-service ordering, instant refunds, recommendations, similarities, search inside the book, associates selling, and third-party products. The list goes on. And these were just the customer-facing innovations. We are not even scratching the surface of what was happening behind the scenes. Amazon started off with a traditional 2-tier architecture, a monolithic stateless application, a BIDS, that was used to serve pages and a whole battery of databases that grew with every new set of product categories, products inside those categories, customers, and countries that Amazon launched in. These databases were a shared resource and eventually became the bottleneck for the pace that we wanted to innovate. Back in 1998, a collective of senior Amazon engineers started to lay the groundwork for a radical overhaul of Amazon's architecture to support the next generation of customer-centric innovation. A core point was separating the presentation layer, business logic and data, while ensuring that reliability, scale, performance, and security met an incredibly high bar, and keeping costs under control. Their proposal was called the Distributed Computing Manifesto. I'm sharing this now to give you a glimpse at how advanced the thinking of Amazon's engineering team was in the late 90s. They consistently invented themselves out of trouble, scaling a monolith into what we would now call a service-oriented architecture, which was necessary to support the rapid innovation that has become synonymous with Amazon. One of our leadership principles is to invent and simplify. Our engineers really live by that motto. Things change. One thing to keep in mind as you read this document is that it represents the thinking of almost 25 years ago. We have come a long way since. Our business requirements have evolved, and our systems have changed significantly. You may read things that sound unbelievably simple or common. You may read things that you disagree with, but in the late 90s these ideas were transformative. I hope you enjoy reading it as much as I still do. The full text of the Distributed Computing Manifesto is available below. You can also view it as a PDF. Distributed Computing Manifesto created May 24, 1998. Revised July 10, 1998. Background. It is clear that we need to create and implement a new architecture if Amazon's processing is to scale to the point where it can support 10 times our current order volume. The question is, what form should the new architecture take, and how do we move towards realizing it? Our current two-tier client-server architecture is one that is essentially data-bound. The applications that run the business access the database directly and have knowledge of the data model embedded in them. This means that there is a very tight coupling between the applications and the data model, and data model changes have to be accompanied by application changes, even if functionality remains the same. This approach does not scale well and makes distributing and segregating processing based on where data is located difficult, since the applications are sensitive to the interdependent relationships between data element. Key concepts. There are two key concepts in the new architecture we are proposing to address the shortcomings of the current system. The first is to move toward a service-based model, and the second is to shift our processing so that it more closely models a workflow approach. This paper does not address what specific technology should be used to implement the new architecture. This should only be determined when we have determined that the new architecture is something that will meet our requirements and we embark on implementing it. Service-based model. We propose moving towards a three-tier architecture where presentation, client, business logic and data are separated. This has also been called a service-based architecture. The applications, clients, would no longer be able to access the database directly, but only through a well-defined interface that encapsulates the business logic required to perform the function. This means that the client is no longer dependent on the underlying data structure or even where the data is located. The interface between the business logic in the service and the database can change without impacting the client, since the client interacts with the service through its own interface. Similarly, the client interface can evolve without impacting the interaction of the service and the underlying database. Services, in combination with workflow, will have to provide both synchronous and asynchronous methods. Synchronous methods would likely be applied to operations for which the response is immediate, such as adding a customer or looking up vendor information. However, other operations that are asynchronous in nature will not provide immediate response. An example of this is invoking a service to pass a workflow element onto the next processing node in the chain. The requester does not expect the results back immediately, just an indication that the workflow element was successfully queued. However, the requester may be interested in receiving the results of the request back eventually. To facilitate this, the service has to provide a mechanism whereby the requester can receive the results of an asynchronous request. There are a couple of models for this: polling or callback. In the callback model, the requester passes the address of a routine to invoke when the request completed. This approach is used most commonly when the time between the request and a reply is relatively short. A significant disadvantage of the callback approach is that the requester may no longer be active when the request has completed, making the callback address invalid. The polling model, however, suffers from the overhead required to periodically check if a request has completed. The polling model is the one that will likely be the most useful for interaction with asynchronous services. There are several important implications that have to be considered as we move toward a service-based model. The first is that we will have to adopt a much more disciplined approach to software engineering. Currently much of our database access is ad hoc, with a proliferation of parallel scripts that to a very real extent run our business. Moving to a service-based architecture will require that direct client access to the database be phased out over a period of time. Without this, we cannot even hope to realize the benefits of a 3-tier architecture, such as data location transparency and the ability to evolve the data model without negatively impacting clients. The specification, design, and development of services and their interfaces is not something that should occur in a haphazard fashion. It has to be carefully coordinated so that we do not end up with the same tangled proliferation we currently have. The bottom line is that to successfully move to a service-based model, we have to adopt better software engineering practices and chart out a course that allows us to move in this direction while still providing our customers with the access to business data on which they rely. A second implication of a service-based approach, which is related to the first, is the significant mindset shift that will be required of all software developers. Our current mindset is data-centric, and when we model a business requirement, we do so using a data-centric approach. Our solutions involve making the database table or column changes to implement the solution, and we embed the data model within the accessing application. The service-based approach will require us to break the solution to business requirements into at least 2 pieces. The first piece is the modeling of the relationship between data element, just as we always have. This includes the data model and the business rules that will be enforced in the service or services that interact with the data. However, the second piece is something we have never done before, which is designing the interface between the client and the service, so that the underlying data model is not exposed to or relied upon by the client. This relates back strongly to the software engineering issues discussed above, workflow-based model and data domaining. Amazon's business is well suited to a workflow-based processing model. We already have an order pipeline that is acted upon by various business processes from the time a customer order is placed to the time it is shipped out the door. Much of our processing is already workflow oriented, albeit the workflow elements are static, residing principally in a single database. An example of our current workflow model is the progression of customer_orders through the system. The condition attribute on each customer_order dictates the next activity in the workflow. However, the current database workflow model will not scale well because processing is being performed against a central instance. As the amount of work increases, a larger number of orders per unit time, the amount of processing against the central instance will increase to a point where it is no longer sustainable. A solution to this is to distribute the workflow processing so that it can be offloaded from the central instance. Implementing this requires that workflow element like customer_orders would move between business processing nodes that could be located on separate machines. Instead of processes coming to the data would travel to the process. This means that each workflow element would require all of the information required for the next node in the workflow to act upon it. This concept is the same as one used in message-oriented middleware, where units of work are represented as messages shunted from one node, business process, to another. An issue with workflow is how it is directed. Does each processing node have the autonomy to redirect the workflow element to the next node based on embedded business rules, autonomous, or should there be some sort of workflow coordinator that handles the transfer of work between nodes, directed? To illustrate the difference, consider a node that performs credit card charges. Does it have the built-in intelligence to refer orders that succeeded to the next processing node in the order pipeline and shunt those that failed to some other node for exception processing? Or is the credit card charging node considered to be a service that can be invoked from anywhere and which returns its results to the requester? In this case, the requester would be responsible for dealing with failure conditions and determining what the next node in the processing is for successful and failed requests. A major advantage of the directed workflow model is its flexibility. The workflow processing nodes that it moves work between are interchangeable building blocks that can be used in different combinations and for different purposes. Some processing lends itself very well to the directed model. For instance, credit card charge processing, since it may be invoked in different contexts. On a grander scale, DC processing considered as a single logical process benefits from the directed model. The DC would accept customer orders to process and return the results, shipment, exception conditions, etc., to whatever gave it the work to perform. On the other hand, certain processes would benefit from the autonomous model if their interaction with adjacent processing is fixed and not likely to change. An example of this is that multi-book shipments always go from pick list to rebin. The distributed workflow approach has several advantages. One of these is that a business process such as fulfilling an order can easily be modeled to improve scalability. For instance, if charging a credit card becomes a bottleneck, additional charging nodes can be added without impacting the workflow model. Another advantage is that a node along the workflow path does not necessarily have to depend on accessing remote databases to operate on a workflow element. This means that certain processing can continue when other pieces of the workflow system, like databases, are unavailable, improving the overall availability of the system. However, there are some drawbacks to the message-based distributed workflow model. A database-centric model, where every process accesses the same central data store, allows data changes to be propagated quickly and efficiently through the system. For instance, if a customer wants to change the credit card number being used for his order, because the one he initially specified has expired or was declined, this can be done easily, and the change would be instantly represented everywhere in the system. In a message-based workflow model, this becomes more complicated. The design of the workflow has to accommodate the fact that some of the underlying data may change while a workflow element is making its way from one end of the system to the other. Furthermore, with classic queue-based workflow it is more difficult to determine the state of any particular workflow element. To overcome this, mechanisms have to be created that allow state transitions to be recorded for the benefit of outside processes without impacting the availability and autonomy of the workflow process. These issues make correct initial design much more important than in a monolithic system, and speak back to the software engineering practices discussed elsewhere. The workflow model applies to data that is transient in our system and undergoes well-defined state changes. However, there is another class of data that does not lend itself to a workflow approach. This class of data is largely persistent and does not change with the same frequency or predictability as workflow data. In our case, this data is describing customers, vendors, and our catalog. It is important that this data be highly available and that we maintain the relationships between these data, such as knowing what addresses are associated with a customer. The idea of creating data domains allows us to split up this class of data according to its relationship with other data. For instance, all data pertaining to customers would make up one domain, all data about vendors another, and all data about our catalog a third. This allows us to create services by which clients interact with the various data domains and opens up the possibility of replicating domain data so that it is closer to its consumer. An example of this would be replicating the customer data domain to the UK and Germany so that customer service organizations could operate off of a local data store and not be dependent on the availability of a single instance of the data. The service interfaces to the data would be identical, but the copy of the domain they access would be different. Creating data domains and the service interfaces to access them is an important element in separating the client from knowledge of the internal structure and location of the data. Applying the concepts. DC processing lends itself well as an example of the application of the workflow and data domaining concepts discussed above. Data flow through the DC falls into three distinct categories. The first is that which is well suited to sequential queue processing. An example of this is the received items queue filled in by receive. The second category is that data which should reside in a data domain either because of its persistence or the requirement that it be widely available. Inventory information, bin items, falls into this category as it is required both in the DC and by other business functions like sourcing and customer support. The third category of data fits neither the queuing nor the domaining model very well. This class of data is transient and only required locally, within the DC. It is not well suited to sequential queue processing, however, since it is operated upon in aggregate. An example of this is the data required to generate pick lists. A batch of customer shipments has to accumulate, so that pick list has enough information to print out picks according to shipment method, etc. Once the pick list processing is done, the shipments go on to the next stop in their workflow. The holding areas for this third type of data are called aggregation queues, since they exhibit the properties of both queues and database tables, tracking state changes. The ability for outside processes to be able to track the movement and change of state of a workflow element through the system is imperative. In the case of DC processing, customer service and other functions need to be able to determine where a customer order or shipment is in the pipeline. The mechanism that we propose using is one where certain nodes along the workflow insert a row into some centralized database instance to indicate the current state of the workflow element being processed. This kind of information will be useful not only for tracking where something is in the workflow, but it also provides important insight into the workings and inefficiencies in our order pipeline. The state information would only be kept in the production database while the customer order is active. Once fulfilled, the state change information would be moved to the data warehouse, where it would be used for historical analysis, making changes to in-flight workflow element. Workflow processing creates a data currency problem, since workflow element contain all of the information required to move on to the next workflow node. What if a customer wants to change the shipping address for an order while the order is being processed? Currently, a CS representative can change the shipping address in the customer_order, provided it is before a pending_customer_shipment is created, since both the order and customer data are located centrally. However, in a workflow model, the customer order will be somewhere else being processed through various stages on the way to becoming a shipment to a customer. To effect a change to an in-flight workflow element, there has to be a mechanism for propagating attribute changes. A publish and subscribe model is one method for doing this. To implement the P&S model, workflow processing nodes would subscribe to receive notification of certain events or exceptions. Attribute changes will constitute one class of events. To change the address for an in-flight order, a message indicating the order and the changed attribute would be sent to all processing nodes that subscribed for that particular event. Additionally, a state change row would be inserted in the tracking table indicating that an attribute change was requested. If one of the nodes was able to effect the attribute change, it would insert another row in the state change table to indicate that it had made the change to the order. This mechanism means that there will be a permanent record of attribute change events and whether they were applied. Another variation on the P&S model is one where a workflow coordinator, instead of a workflow processing node, affects changes to in-flight workflow element instead of a workflow processing node. As with the mechanism described above, the workflow coordinators would subscribe to receive notification of events or exceptions and apply those to the applicable workflow element as it processes them. Applying changes to in-flight workflow elements synchronously is an alternative to the asynchronous propagation of change requests. This has the benefit of giving the originator of the change request instant feedback about whether the change was affected or not. However, this model requires that all nodes in the workflow be available to process the change synchronously and should be used only for changes where it is acceptable for the request to fail due to temporary unavailability. Workflow and DC customer order processing. The diagram below represents a simplified view of how a customer order moved through various workflow stages in the DC. This is modeled largely after the way things currently work, with some changes to represent how things will work as the result of DC isolation. In this picture, instead of a customer order or a customer shipment remaining in a static database table, they are physically moved between workflow processing nodes represented by the diamond-shaped boxes. From the diagram, you can see that DC processing employs data domains for customer and inventory information, true queue for received items and distributor shipments, as well as aggregation queues for charge processing, pick listing, etc. Each queue exposes a service interface through which a requester can insert a workflow element to be processed by the queue's respective workflow processing node. For instance, orders that are ready to be charged would be inserted into the charge services queue. Charge processing, which may be multiple physical processes, would remove orders from the queue for processing and forward them on to the next workflow node when done, or back to the requester of the charge service, depending on whether the coordinated or autonomous workflow is used for the charge service.